All right, next we'll hear from AJ. John, thanks to the organizers for putting together this really awesome workshop. I'm excited to tell you about some of the opportunities I see for AI and catalysis. First, I want to give kind of a big overview of our group for folks who may not know me. We work at the intersection of computational chemistry, data science, and catalysis. Sometimes that just means doing computational chemistry on catalysts, sort of old school computational catalysis. And so we've studied a lot of reactions, in particular photocatalytic nitrogen fixation. It's been a fun scientific roller coaster. I'm not going to talk about that today, but happy to talk about that offline. Also, we do a good bit of work on development of features for electrons and atoms. And so this is another area of research in the group I'm not going to talk much about today. What I want to focus on for opportunities is the aspect of our research where we're trying to do computational catalysis without the atomistic models. How can we take experimental data and extract fundamental insight from that? And so before I get into it, I want to give a couple of acknowledgements and quick advertisements. First off, the students, of course, have done all of the work. In particular, Gabriel Guzmão, who is now an alum of the group, was really instrumental in the transient kinetic analysis work we've done. Jagriti Sahu and Si-Hoon Choi didn't necessarily do that work, but they are graduating and are on the job market. So if anyone's looking to hire, they're two very fantastic graduate students. I'm very appreciative to DOE and NSF for funding. And then I want to just give a plug. I've mentioned this Spark DFT code to many of you over the last few days and few years, but this is a really cool effort from Fanish Surya and Ariana's group at Georgia Tech. Exascale capable finite difference DFT code. It's easy to compile. It has two dependencies, MPI and BLAS or MKL, so it's pretty easy to get up and running with. It's free and open source. And we're building in, probably for the next release, we'll have some machine learned force field on the fly, machine learning exchange correlation functional capabilities, as well as a nice Python API and an ASE calculator. So I'm not going to say any more about it, but I'm happy to talk about that offline as well. And so what I do want to talk about today is kind of zooming out and thinking about our strategies for understanding catalysis. We can maybe broadly classify this as bottom up and top down. Bottom up, we've heard a ton about, right? This is basically doing DFT calculations, using atomistic models to try to predict rates and predict observables of catalysis. The fantastic strategy, we've done a lot of this as well. It's great for designing catalysts, but we also know it has some pretty severe limitations if you want to do quantitatively accurate rates. We heard from Johannes and Boris yesterday about issues with exchange correlation errors. And then we also have this existential problem of, do we know if we have the right active site structure? The other way of looking at this is sort of from the top down. Basically, you can measure kinetics and we can fit kinetic models and extract rate parameters that way. The nice thing here is we know that the models match the data. The big problem that we have is that we know that for steady state data, we're going to overfit. We're going to have only one parameter that determines the kinetics, and so this is a challenge. And if we look at how AI impacts these two, I would argue that AI has made a ton of impact on the bottom-up approaches, but significantly less on the top-down. There's been some work done, but I think there's a big opportunity there. So that's kind of what I wanted to talk about today. So transient kinetics is something that we've gotten into. It overcomes some of these challenges for fitting kinetic models. In a transient kinetic system or transient kinetic data set, your data is governed not only by the rate limiting step, but by other steps in the network. So in principle, we can extract more information. We have higher time resolution in transient kinetics. So we can see some of these faster processes that you would miss in a steady state measurement. And they can generally be measured more quickly. So you don't have to wait 12 hours for steady state. You can take measurements in seconds or minutes and generate large volumes of data. Some of the challenges are the math is harder. So how do we actually extract the intrinsic kinetics from these systems that are basically governed by partial differential equations? We have larger data sets, we need more computing power. And then there are some issues, not all of the concepts that we're used to thinking about with steady state kinetics transfer. But nonetheless, we sort of started exploring this idea of, can we extract intrinsic kinetics directly from transient kinetic data? This is a very generic form of a microkinetic model. And so the idea here is it doesn't have to be fully microkinetic. We know we're not going to be able to measure every single elementary process, but can we start thinking about using elementary-like models and extracting those parameters from data? And so Gabriel did some work and developed what he calls kinetics-informed neural networks. For those who are familiar, this is just a physics-informed neural network with a couple of little tricks on site conservation and other things that make it nice for kinetics. And for those who aren't familiar with physics-informed neural networks, the idea is pretty straightforward. We train a neural network with a loss function that tries to optimize two things. First, it tries to make sure that the derivatives of the concentrations, effectively the measured rates, match our underlying kinetic model. And then at the same time, it tries to make sure that the concentrations that come out of the model match the data. The important thing here is that it minimizes both the weights of the neural network as well as the kinetic parameters. So the output of this is not some fancy machine learning model, it's just kinetic parameters. This is basically just kinetic model fitting with a neural network as a numerical method. So we can do this and it basically works. So this is our ABCDE toy problem that Gabriel cooked up. It has adsorption, it has reaction between adsorbates. We tried to make it pretty realistic. We added some noise. We chose kinetic rate constants that spanned about 5 orders of magnitude. So it's reasonably stiff. And what you can see over on the left is that it fits the data relatively well, both for gas phase and surface species. It fits the model pretty well here in the middle. And then most importantly, over here on the right, we can see that the rate parameters that come out are pretty accurate, even over many orders of magnitude. So we tried to make this kind of realistic, but we cheated in one really important way, which is that we told it what the surface concentrations are. And we know in catalysis that we don't usually actually know what the surface concentrations are. We have to measure those through some sort of operando spectroscopy. And so one of the things that we're sort of working toward now is some sort of benchmark for this kind of inverse problem in catalysis that's really representative of the real challenges with experimental data sets. And so this involves complexity and stiffness of the equations. Our idea here was, let's just assume DFT is right. I'm going to create a simple water gas shift model on rhodium-211. I'm going to build a microkinetic model. I'm going to put that inside of a reactor model that looks reasonably close to these praying mantis cells that they actually use for operando spectroscopy. And I'm going to simulate basically a pulsed experiment with the microkinetic model. I'm going to simulate the spectra to go with that. So we're using mass spec fragmentation patterns from NIST, and we're simulating IR spectra for the surface species. And then, try to see if we can fit this. A couple of things that were really important. We also thought about time resolution. So you have different time resolutions for these spectra. Many of these real things that happen with experimental data kind of break the assumptions that the modelers make in their toy models. And so this is kind of what has come out of this. It's a synthetic experimental data set of effectively operando IR spectroscopy of water gas shift on rhodium. It's still really clean by experimental standards. Like I think this would be a dream data set for someone to measure, but it does actually look like real raw data where we have mass spec fragments and IR spectra. The spoiler is that it's really difficult to solve the inverse problem once you take away the information that you don't have in experiments. And so I'm not going to show the results. They were mediocre. And this is not published because my graduate student decided he would spend the last 6 months of his PhD trying to get really good results rather than writing up the results that we have. And now he's graduated. And so I'm slowly trying to turn this into a paper. So if you're interested in learning more about this, shoot me an email. I'm happy to talk more about it. But I just want to conclude by sort of going back to opportunities for AI. And I think this follows really nicely from Wendy's talk. If we think about catalysis as an inverse problem, one of the challenges is that we have all these different areas of knowledge that become important. So obviously we have catalysis, what's the active site, what's the mechanism. There are also big numerical methods challenges. I didn't talk about it at all, but in order to just solve the forward problem to simulate that experimental data, Gabriel had to implement computational singular perturbation theory and do all of these crazy numerical methods just to solve the differential equations. So there's this whole other body of knowledge that you have to have. Spectroscopy is obviously, its own entire field. So Anatoly spoke about that yesterday. And so understanding all of the details of spectra and how that comes together. Reaction engineering, right? Does transport matter? Does it not matter? We've heard a ton about electronic structure theory and how hard all that is. And so I think there's an opportunity here. I don't have any specific ideas, but I think there are opportunities for things like these AI assistants or models that can help us integrate all of this knowledge together to kind of bring multimodal data toward an intrinsic picture of catalysis. And so this was our cover art for this article that we wrote about 8 years ago or 7 years ago now, thinking about kind of how all this information flows together in catalysis. And now I just stamped AI on it. So we haven't figured it out without AI. So maybe AI can sort of help bridge this gap. That's it. Thanks.